Okay, so welcome to section 9.7, which is inverse matrices. Inverse matrices. So what is an inverse? So definition. First, let's define the identity matrix. So the n by n identity matrix denoted by capital I sub n is the matrix with ones along the main diagonal, and zeros everywhere else, and zeros in all other entries. Okay, so for example, I sub 2 is the 2 by 2 matrix that has ones along the main diagonal and zeros everywhere else. So our main diagonal, of course, will be this guy. Maybe I should do this in a lighter color, say yellow or gold. Okay. And similarly, where my I sub 3 would be, really? I sub 3 would be the matrix, a 3 by 3 matrix. That's analogous. So 1, 0, 0, 0, 1, 0, 0, 0, 1. Once again, let's use the yellow. We notice along the main diagonal is ones and everywhere else is 0. That's the identity matrix. So let's note something. So note the identity matrix is the matrix analogy to the scalar 1. That is, i.e. it est, I sub n times the a matrix A is the same as A times the identity matrix, which is the same as A. And we recall that 1 times any number is just itself. So let's recall. Okay, so an augmented matrix, in reduced row echelon form, has solved the system. So what do we mean visually? So say we've got reduced row echelon is 1, 0, 0, 0, 1, 0, 0, 0, 1. Augment. 1 times x is whatever the x value is. 1 times y is whatever the y value is. 1 times z is whatever the z value is. So notice that on the left here, come on, why did I not do this? Okay, oh my goodness, I feel like, so this is the identity sub 3, right? Whereas this right here is the solution to the system. Okay, so definition. Now we'll do the inverse, definition of inverse. So definition. Okay, so an n by n matrix B is the inverse of matrix A denoted by B is equal to A inverse, much like function inverse, if we have that A times B is the same as B times A is the n by n identity matrix. Okay, so for example, show that the following are inverse matrices. Okay, so number 1, let's say we have matrix A is given as, let's do 1, 2, 1, 3. And matrix B is given as 3, negative 2, negative 1, 1. Okay, so let's do A times B. A times B. So that's going to be this matrix here. Let's see if I can get rid of that line. Let's call this blue. And this matrix here, let's get rid of that line and call this guy purple. Okay, so what do we have? Recall, this will be 1 times 3 plus 1 times negative 2. So I've used the first row of A with the first column of B. Then it'll be 2 times 3 plus 3 times negative 2. So in blue, I have all of A, and in purple, I have the first entry and then the second entry. So we could do the same without thinking over here. 1, 2 times negative 1, negative 1. And then plus 1, 3 times 1, 1. Unbelievable. All I want to do is put a square bracket. Okay, so we have that AB will be equal to 3 minus 2 is 1. 6 minus 6 is 0. Negative 1 plus 1 is 0. Negative 2 plus 3 is 1. So that's good, because that's I sub 2. Okay, what about B times A? Well, that's going to be matrix B here in purple times matrix A here in blue. Okay, so what's that going to be? Well, now it's going to be the purple matrix 3, -2 times the first entry 1, 1 plus -1, so I guess I'll make that a negative. -1, 1 times the second entry 2, 2 in that first column. Then again, 3, -2 times entry 1, 1. Let's do minus and plus. So the next entries will be -1 and +1. And the final entry there is 3 and 3. Oops, why does that do that? Sorry. Okay, so we have that B times A will be the matrix. Let's see, 3 minus 2 is 1, -2 plus 2 is 0, 3 minus 3 is 0, and -2 plus 3 is 1. So that's equals to I sub 2, check mark. So therefore, A times B is equal to B times A is equal to the identity matrix, which implies, of course, oh, why is this dashed? This implies, of course, that B is A inverse. B is equal to the inverse of matrix A. And vice versa. Okay, that was a long one. Let's do subscript number 2. So now we have matrix A is going to be, let's do 7, 5, 3, 2. Let's have matrix B be the matrix. Let's do -2, 5, 3, and -7. Okay, so once again, if we have A times B, this will give us blue times purple so without further ado, I'll stop showing explicit, well, maybe I'll show it just for this one. So 7 and 5 times -2, plus 3 and 2 times 5 and 5. Then we have 3 and 2. No, we don't. I'm an idiot. Then we have 7 and 5 once again. Times, where am I? 3 and 3. And then we have plus 3 and 2 times -7 and -7. Okay, so what do we get? We get that A times B is going to be equal to, let's see, -14 plus 15 is 1, -10 plus 10 is 0, 21 minus 21 is 0, 15 minus 14 is 1. So that is indeed I sub 2, check mark. But let's show it the other way. So B times A B purple times blue Okay, so what does that give us? Okay, so it's going to be minus 2 and 5, both times 7, to which we're adding and subtracting because it's 3 and negative 7, times 5 and 5 for the first column. Then once again we have negative 2 and 5, now times 3 and 3, plus and minus because that 7 is negative. So we're going to have 3 and minus 7 times 2 and 2 for the second column. Okay, so what do we get for B times A? We get, let's see, negative 14 plus 15 is 1. 35 minus 35 is 0. Negative 6 plus 6 is 0. And 15 minus 14 is 1. So this is indeed I sub 2, check mark. So therefore we have that A times B is the same as B times A. Is the same as the 2 by 2 identity matrix, which implies, of course, that B is indeed A inverse and vice versa. Okay, let's do one more, number 3. So let's say we have that A is equal to, I think I might need to move this down just one line. It seems a bit cramped here. Here we go. So let's have A be 2, 3, 3, 5. And let's have B be 5, negative 3, negative 3, 2. Okay. So once again, we'll do A times B will be A, change this to blue, times B, change this to purple. Then I can underline now, B is in purple, A is in blue. Okay, so what do we get? We get, let's see if we can do this in our heads at this point. 2 times 5 is 10, minus 3 times 3 is 9. 10 minus 9 is 1. Then 3 times 5 is 15, minus 5 times 3 is 15, so that's 0. Then 2 times minus 3 is negative 6, plus 3 times 2 is 6, is 0. Then 3 times negative 3 is negative 9, plus 5 times 2 is 10. Okay, so that is indeed I sub 2, check mark. So let's go the opposite way. So B times A. That's going to be purple guy first. Oops, without, I'm missing one of the, so purple times blue, and what is the entry in the first row and the first column? Looks like it's going to be 5 times 2 is 10, minus 3 times 3 is 9, 10 minus 9 is 1. Then the second row in the first column will be minus 6 plus 6 is 0. Then first row, second column, 15 minus 15 is 0. Then second row, second column will be negative 9 plus 10 is 1. Okay, so that is indeed I sub 2. So therefore these two imply B is indeed A inverse. Okay, so hopefully that makes sense. Okay, so now we've got some fun stuff to do. So I'm only going to do, I think, one example of this, and then we'll do it an easier way, because this is a miserable way. So finding the inverse of an n by n matrix. Okay, so step 1 would be to express A in an augmented matrix. With I sub n. Then number 2, use elementary row operations. Row operations. To get A to I sub n. Then step 3, the right-hand side of the augment. The right-hand side of the augment is A inverse. Okay, so this is a lot. So what I'd like to do is only do one example because it's so miserable. So, but first, what do we mean by this? So, for example, that is, it asked what you're going to do is you're going to have your A, and you're going to augment it. Okay. Actually, let me color this better. A, and we will augment A with the identity matrix I sub n. Then what you're going to do is use elementary row operations. So elementary row operations. And your goal is to arrive at an augmented system with now I sub n on the left. Actually, let me keep it. Let's call this pink. I sub n on the left. Augment, because your goal is to get I sub n on the left. Why does this not autocorrect? And what you'll have on the right, after all is said and done, should be A inverse, if you've done it right. And that's a big if. This method is not the most efficient way to do it. Oh, come on. Steve Jobs. Okay, whatever. At this point, all I want to do is create one line that's connected in a bracket. Why is that so difficult? Okay, holy free holy. Okay, so for example, let A be equal to, let's use one of these guys. Shall we use 2, 3, 3, 5? Let's use that one, what the heck. So 2, 3, 3, 5. 2, 3, 3, 5. So find A inverse using an augmented matrix. Okay, let's see if I can move this a bit to the left. Okay, so what I'm going to do is I'm going to set up an augmented matrix here. So I've got A, 2, 3, 3, 5. I'm going to augment that with the identity matrix 1, 0, 0, 1. And I'm going to try to use elementary row operations to get the identity matrix on the left. Okay, so the first step is I want a 1 in the place where 2 is. So let's do 2 times row 1 minus row 2. So that's going to give us 2 times 2 minus 3. Then 2 times 3 minus 5. Augment 2 times 1 minus 0 and 2 times 0 minus 1. Okay, so we still have 3, 5, 0, and 1. Okay, so what do we get then? We get 4 minus 3 is 1. 6 minus 5 is 1. 5, augment. We get 2 minus 0 is 2. 0, oh shoot, these were supposed to be in pink. Sorry. Okay, and then we get 0 minus 1 is negative 1 and 1. Okay, so now I claim if I do row 2 minus 3 times row 1, that'll get me the 0 where I want it. So we have row 2 minus 3 times row 1. Row 2 minus 3 times row 1. Augment row 2 minus 3 times row 1. Row 2, oh, why does it always do that? Where am I? Row 2, which is a 1, minus 3 times row 1, which is negative 1. Okay, so row 1 is still 1, 1, 2, negative 1. So what do we get then? We get 1, 3 minus 3 is 0. 1, 5 minus 3 is 2. Augment 2, 0 minus 6 is negative 6. Negative 1 and 1 plus 3 is 4. I'm just going to go ahead and do 1/2 of row 2. So that'll be 1/2 times 0, 1/2 times 2, augment, 1/2 times -6, and 1/2 times 4. My first row is still 1, 1, 2, -1. Okay, so what do we get? We get 1, 0, 1, 1, augment, 2, -3, -1, 2. And it looks like I'm just one step away. So I claim that if I do row 1 minus row 2, that'll get me the 0 in that last spot. So row 1 minus row 2. Row 1 minus row 2, augment, row 1 minus row 2, row 1 minus row 2. Okay, and row 2 is just 0. What are you doing, kitty? 1, -3, and 2. Don't know if I'll have notes for the next section because my cat is sitting on them. I know. Okay, so we have 1, 0, 0, 1, augment. I know. 5 minus 3, minus 3 and 2. So guess what? I claim that this is A inverse right here. And we can check because we actually had A inverse. 5 minus 3 minus 3 and 2. Yeah, that looks like it. So check mark. Okay, so A inverse. Actually, let me write it in blue. So A inverse is going to be the matrix 5, -3, -3, and 2. This was a very, very cumbersome way of finding the inverse. So that's why I'm only doing one example. Now, let's move on to maybe an easier way to do this. Do you know what? I'm going to keep this in pink only because I have a definition next and I don't want blue next to blue. So definition. So the determinant of a 2 by 2 matrix A. Let's have A is the real number found by taking the difference and the products of the main and alternate diagonals. Main and alternate diagonal entries. So that is, if A is equal to, denoted by, I forgot to denote it by what looks like the absolute value of A, but since it's a matrix, the absolute value analogy becomes a determinant. So if A is equal to the matrix A, B, C, D, then this implies the determinant of A is going to be the products of the main diagonal. Oh, maybe I should make that a different color. So A times D minus the product of the alternate diagonal. C times B. And that is that's a real number. So the determinant is actually a real number. Okay, so theorem, once we know that, so let's maybe I need to move down here. Let's let A be the 2 by 2 matrix, A, B, C, D, such that the determinant of A is not equal to 0. Then A inverse will be 1 divided by the determinant of A times the matrix that swaps the main diagonal and negates the alternate diagonal. What? Hold on. Should be A, B, C, D. Wow, cannot. So this is... So A and D, and then minus B minus C. Sorry. I'm having issues. This is the second time I've recorded this whole section because it got messed up at the end. Okay. So I'm a bit tired, as usual. What else is new? Notice how much easier this is. So for example, I know, kitty. So find the inverse. The inverses of the following matrices. Okay, so number 1, let's say we have that A is equal to 4, 5, 2, 3. Okay, so the determinant of A, which has straight up and down lines, not bracketed lines. That's why it's so important that I've been making those bracketed lines, because straight up and down means something else. It means a determinant. So this is going to be the main diagonal entries here. 4, 3. Actually, we did that in pink, didn't we? 4, 3. So 4 times 3 minus alternate diagonal entries 2 times 5. So that's going to be 12 minus 10 is 2. I claim that A inverse is just going to be 1 over the determinant of A times the matrix that swaps the main diagonal. So this will now be 3 and 4 and negates the alternate diagonal. So this will now be -2 and -5. So that's going to be what? That's going to be 1 over 2 times the matrix 3, -5, -2, 4. That's kind of nice. Let's see, let's check. I always want to check. And I'll just do A times A inverse. So A times A inverse, well, that's going to be, let's take out the 1/2 in front. A is the matrix 4, 5, 2, 3, 4, 5, 2, 3. Once again bracketed, because we are dealing with the actual matrix, not the determinant. So 4, 5, 2, 3 times the matrix 3, -5, -2, 4. Okay, so what do we get? We get 1/2 times the matrix. Let's do the multiplication here for these guys. And what do we get? 4 times 3 is 12, minus 2 times 5 is 10, so that's 2. 5 times 3 is 15, minus 15 is 0. 8 minus 8 is 0, and -10 plus 12 is 2. So dividing each entry in this matrix by 2, we get 1, 0, 0, 1, check mark. They are inverses of one another. Okay, so subscript number 2. Let's say we have that A is equal to, let's do 1, 2, 3, 4. 3, 4. Okay, so I claim that the determinant of A, which has straight up and down lines, 1, 2, 3, 4, is going to be product of the main diagonal, which is 1 times 4, minus the product of the alternate diagonal, which is going to be 3 times 2. So 4 minus 6, is -2. Okay, so A inverse, I claim, will be 1 over the determinant of A times the matrix that swaps the main diagonal entries and negates the alternate diagonal entries. So I claim that this will be 1 over 2, -2, times the matrix 4, -2, -3, 1. Well, let's check that out. So let's check. But that was so much easier than doing that Gaussian elimination. So let's check. So A times A inverse. I'm going to go ahead and bring the constant -1/2 in front. Matrix A was 1, 2, 3, 4. 1, 2, 3, 4. Jeez. Okay, I know Steve Jobs did not come up with this app. So maybe he's not in hell for that one. Okay. And then we have 4, -2, -3, and 1. Okay. So what we get then is -1/2 times the product of these two matrices, which will be 4 minus 6 is -2. 8 minus 8 is 0. -3 plus 3 is 0. -6 plus 4 is -2. So dividing each entry by -2, we do indeed get the identity matrix. So check mark. 1, 0, 0, 1. It works. Okay. So number 3. Let's say we have that A is equal to, let's do 7, 5, 3, 2. Okay, so I claim that the determinant of A, which has straight up and down lines, 7, 5, 3, 2. Will be, okay, so main diagonal entries are going to be 7 times 2 minus alternate diagonal entries will be 3 times 5. Okay, so 14 minus 15 is -1. Okay, so A inverse, I claim, will be 1 over the determinant of A times the matrix that swaps the main diagonal entries of A and then negates the other two entries. So -3 minus 5. So I claim that this will be -1, because it's 1 over -1 is the same as -1, times the matrix 2, -5, -3, 7. Well, -1 is easy enough to push in, so I claim that this is the matrix -2, +5, +3, and -7. Okay, so let's check. So much easier. So I only did one of those examples of the terrible. So A times A inverse will be we have 7, 5, 3, and 2, and times the matrix -2, 5, 3, and -7. So this gives us -14 plus 15 is 1, -10 plus 10 is 0, 21 minus 21 is 0, 15 minus 14 is 1, and that is what we're looking for. Okay. But now we need to solve a system with inverses. So let's do that. So solving a system with inverse matrices. Okay, so given the system AX plus BY is equal to H, cx plus dy is equal to k. Then where do I want to put that? A is going to be the matrix of coefficients, AC and BD. X is going to be the matrix of variables, X, Y. And B is going to be the matrix of constants, H and K. Okay, so let's consider something. So consider so if we were to multiply A times X in the above, we would get this matrix A, B, C, D times this matrix here. So that's a 2 by 2 times a 2 by 1, so that does work. And that gives us what matrix? That gives us AX plus BY and CX plus DY. And we know that that's equal to B, right? We know that AX plus BY is the same as H. And we know that CX plus DY is the same as K from the system above, right? Okay, so what is that? That's B. Okay, so let's note then. We have AX is equal to B. Well, this implies that A inverse AX is equal to A inverse B. And this is left multiplication. Left multiplication by A inverse. Remember, it's not commutative. If I multiply on the left, that's it. I multiply on the left. So now I claim that A inverse is I. So this is still A inverse B on the right. I really can't do anything about that. And how did I get I? And that's a property of inverse matrices. Right, because any matrix times its inverse is the identity. So we get that X is equal to A inverse B. So why can I omit the identity? And this is a property of the identity, Because when you multiply by the identity matrix, it doesn't change anything. It's like multiplying by 1. Okay, so we're going to use that. So, theorem. So, given an n by n system of equations with coefficient matrix A don't want to say and, let's say variable matrix X, variable matrix capital X, and constant coefficient matrix B. Matrix B. If the determinant of A is not equals to 0, then X will be A inverse B. So that's how we're going to solve systems now, until we get to Cramer's rule in the next section. So for example, so solve the following systems using inverse matrices. So solve the following systems using inverse matrices. So number 1, let's say we have 7x plus 3y is 16 and 5x plus 2y is 11. Okay, so I claim that the coefficient matrix A is going to be 7, 5, 3, 2. So this means that A inverse is going to be 1 over the determinant. So let me draw this a bit. 1 over the determinant. Well, the determinant is 14 minus 15 times the matrix. It swaps the main diagonal and negates the alternate diagonal. And since that's a -1 there on the outside, that fraction is just going to be -2, 5, 3, and -7, which we already knew. We've done this before. Okay, I know that B is the 2 by 1 matrix of coefficients, or of constants rather. Why is this not auto-correcting? Oh, you for fuck's sake. Okay. 16, 11. Okay, and of course X is what we're looking for. So I claim that X is equal to A inverse times B. So that's just going to be -2, 5, 3, and -7 times B, which is 16 and 11. Why my eye is hurting like crazy. Okay, so what do we get? So what we get then is negative 32 plus 33. It's going to be 1. And 15 times 16. Okay, well, 5 times 16. 5 times 10 is 50, and 5 times 6 is 30. So 5 times 16 is 80, minus 77. So 80 minus 77 is 3. So this is x, which is actually xy. So x, I don't know, did I show that to you? Yeah, it's xy, right? So this implies that the point where these two lines meet in the plane will be at 1, 3. That's the solution. Isn't that nice? Look at that. That was quick. Inverse matrices is amazing. Cramer's rule is equally amazing, but that's the next section. Okay, so let's do a couple more. So let's say we have 2x minus 3y is 1, and 5x minus 7y is 3. Okay, so the matrix of coefficients is going to be 2, 5, negative 3, negative 7. Okay, so this implies that A inverse is 1 over the determinant. The determinant will be negative 14 plus 15. And times a matrix that swaps the main diagonal and negates the alternate diagonal. So that just turns out to be a 1 on the outside. So we get that A inverse is minus 7, minus 5, 3, and 2. Okay, and B, of course, is the... What color did I use for B? Let's use... Okay, so B is the constant coefficients, which are 1 and 3. So in order to find x, the variables, x is just A inverse times B. So that's going to be negative 7, negative 5, 3, and 2 times 1 and 3 Okay, so what do we get here? We get negative 7 plus 9 is 2. We get negative 5 plus 6 is 1. So 2, 1. The solution here is x, y is 2, 1. That's the point where these two lines meet. Okay, let's do third time's the charm, and that'll be it for this section and this evening because my butt hurts from sitting. So 6x plus 5y is equal to 19, and x plus 3y is equal to 14. Okay, so we have A, the matrix of coefficients, is going to be 6 and 1, then 5 and 3. So this implies that A inverse will be 1 over the determinant, and the determinant is going to be 18 minus 5 times the matrix that swaps the main diagonal and negates the alternate diagonal. So this is going to be 113 on the outside over 3, negative 1, negative 5, 6. And we know that B, the matrix of constant coefficients, is 19 and 14. So X, which is A inverse B, be 1/13 times the matrix 3, -1, -5, and 6 times the matrix 19 and 14. Okay, so we get 1/13. Let's calculate the product of these two matrices. So 3 times 19, well, if it were 20, 3 times 20 is 60, but I'm 3 shy, so that's 57, minus 5 times 14. Well, 5 times 10 is 50, and 5 times 4 is 20. So that's going to be what? So that's going to be 57 minus 70. So 57 minus 70 is -13. Okay, so now we have -19 plus 6 times 14. So that's going to be 60 plus 24 is 84. 84 minus 19. So that would be 65. Oops. Okay, so what do we get? 13 goes into -13, -1 times. So let's see, 26. 13 times 2 is 26. If I add another 13, that's going to be 39. If I add another 13 after that, that's going to be 52. And if I add another 13 after that, that's going to be 65. So what was that, 5? Okay, so I claim that we get the point. -1, 5 is the solution in the plane where these two guys meet. And I think I've had enough of this section. I'll see you in the next.